Hey everyone, I'm super excited to be presenting to you all today about online machine learning for streaming data. I'm the founder of Bytewax, which is an open source Python stream processor that you will get to see in action here today. Prior to starting Bytewax, I worked on data science and machine learning problems, from algorithms to infrastructure. I started at a speech technology company and then moved on to developer tools at Heroku and GitHub. It was at GitHub where I experienced the pain of trying to use machine learning to power real-time experiences. This ultimately led to the founding of Bytewax to try and help solve that problem. We've got quite a bit of ground to cover today, but by the end of this presentation, you should be able to reason about the components of a streaming system, understand online machine learning, and know how to build an end-to-end IoT anomaly detection system with a dashboard to visualize what's going on. So let's kick this off with an overview of streaming. Streaming data is continuously generated and an unbounded data set. The data can be varied from unstructured to structured, and it can be generated from multiple sources. It is often used to power real-time applications. To manage streaming data, we use streaming systems with a storage and a compute layer. The streaming data will be produced to the streaming storage layer, and then a compute layer is then used to process that data, and the data is sent or consumed by a downstream system, which we can refer to as a subscriber, receiver, or a sink. The storage layer provides consistency, replayability, ordering, and real-time performance. The processing layer provides the ability to consume the data, and run compute operations on it. Aggregations, transformations, windowing, etc. And all this is at high throughput and low latency. Across both systems, scalability, fault tolerance, and durability are generally required and also hard to solve. Core to streaming systems is the message broker. The message broker facilitates receiving messages and putting them in a queue or log, which is the data structure they are stored in, and then facilitates passing the message downstream to a receiver. Message brokers generally exist in two main categories based on the pattern of read and write. These are publish, subscribe, and point-to-point systems. In a publish, subscribe, or pub-sub system, you have many publishers writing messages to the streaming storage. These are generally organized by topics. Then, on the other side, you can have many subscribers reading the same message. In this case, you can see they're all reading message A. In this pattern, the burden of determining whether a message has been read is on the subscribers. Common systems that use this pattern are Kafka, Red Panda, Pulsar, Kinesis, and Google PubSub. Publish-subscribe systems benefit from the many consumer design and can have a higher throughput. They also generally have different data retention policies due to this design. Telemetry, event-driven applications, and logging transactions are all use cases that fit this pattern really well. Point-to-point systems can also have many services sending messages to them. But in the point-to-point system, you generally don't have the ability to have many receivers getting the same message. So you can see ABC here and then ABC being received. In these systems, the burden is on the message broker, which was sitting in the middle here, to determine whether a message was read. So usually there's some sort of acknowledgement from the receiver that the message has been received and processed. With these systems, you generally don't keep messages around to replay them. Common systems are AWS SQS, RabbitMQ, and Redis Q. Due to the complexity of the fact that the broker is handling those acknowledgements, the throughput is generally lower with point-to-point systems. Microservice-based applications are a fairly common application for point-to-point systems. Core to the stream processing layer that we saw earlier is a category of data processing software called stream processors. There are many different stream processors available, and the main difference is whether they are stateful or not, and whether the interface is imperative or declarative. Some of the more common stream processors are Flink and Spark, structured streaming, with new options becoming available like Bytewax, Arroyo, Quix, and Benthos. Stream processor generally work in a way that the worker, seen here, consumes data as it available from the streaming storage. And this can be parallelized with more workers if the storage is capable of partitioning the data, as you can see here. The workers in a stateful system will then be able to transform the data with windowing or aggregation functions. The workers also most likely need to communicate in order to get the right data to the right worker so that the computations can be correct. Once the data is processed, it is then written downstream to a storage sink. This might be back to the streaming storage or to a database. Now, this is a pretty good segue into online machine learning, because an online machine learning system will run inside that processing layer and requires a stateful stream processor. So a brief introduction to online machine learning, sorry. Online machine learning is a subset of online algorithms where the model is trained and updated one datum at a time, which is in contrast to batch methods that will use an entire batch of data to train the model. It is best fit for unsupervised methods like hash-based trees, which we'll be using today. It can also be quite useful when you have data that doesn't fit into memory, so you can process the data in smaller batches. And in addition, online algorithms or online machine learning are particularly useful when you are working with unbounded data like you do in streaming use cases. Another reason we might choose to use online machine learning is to take advantage of its ability to adapt to dynamic systems, since it is constantly learning. So if our data has a tendency to change the average over time, our model can react to that. For online machine learning on streaming data, the model representation needs to be kept in state, and hence the necessity for a stateful stream processor. So you're probably using some of these online machine learning systems in your day-to-day life. Maybe it's content personalization on Netflix or recommendations from Amazon. Or maybe it's when you call your Uber and you receive a dynamic price and an instant ride matched with driver. Many of these examples of online machine learning all have something in common, which is that the product or service benefits from understanding and reacting to the world in real time. You can take, for example, this algorithmic trading, the example down in the right corner here, where trading bots compete for profit in real time. Or the Uber example, where Uber competes against, say, Lyft or another ride-sharing company or a traditional taxi to price rides appropriately and match drivers to drivers in real time. Whoever can have a better understanding of the whole situation fastest can provide the best price and find the best driver for the best rider. So the example that I haven't mentioned yet that we're going to work with today is anomaly detection. And anomaly detection is a very common application of online machine learning, and it can be modified for a variety of use cases. So let's put some of these components to work. Today, we're going to build a system that leverages online machine learning to do anomaly detection on streaming data that is coming from temperature sensors. In our example, which is contrived and will have randomly generated data, we can imagine our temperature sensors, though, are in a warehouse or maybe in a manufacturing facility. And we want to know as soon as possible if the temperature has changed so we can investigate what's going on. If we had a dynamic environment and we were only worried about the delta of the temperature, or we had different ideal ranges for each sensor, this would be the most efficient way to solve our problem. So to do this, we will use generated sensor data that is sent to our streaming storage layer, and then we'll then consume that in our stream processor to do anomaly detection. And finally, we'll then plot our data to a dashboard so we can view our system running in real time. For our storage layer, we will set up Red Panda, which is a Kafka API compatible streaming platform that is very easy to use and install. And it's also quite performant. For the stream processing layer, we'll be using Bytewax, which is a Python stream processing framework. And we'll use River as the online machine learning library, which has a number of algorithms that are easy to use in the library. And finally, we'll use a tool called Rerun, which is a nice visualization library that provides a Python interface for logging points and a ROS processing engine that makes it very, very performant. All right, to get started here, what we're going to do is we're going to run Red Panda in a Docker container. And we'll also run this handy tool that Red Panda has called console, also in a container. So we'll have both of these in a Docker Compose YAML file, and we'll be able to set that up with one command, Docker Compose up. And then we can go in and check on what's going on in our cluster. So to get started, let's first run Okay, so Red Panda is now running. So we can click on localhost 8080, and we can go in and check out what's going on in our cluster. We can see that it's up and running. We don't have Kafka Connect. We have nothing in our cluster right now. We have one broker. If we go over to our topics, we can delete topics, we can add topics, we can introspect topics. So we're going to create a topic. We're not going to do it from here. We're going to use a helper, Python helper script. We're going to create a topic, and then we're going to start generating some sensor data and writing it to this topic. So let's just do a quick sample of that. So we'll run our helper file, which is just a Python script that essentially chooses some, or will randomly generate some sensor data between a certain temperature and write it to the topic. So run that Python file. So let's run it for a few seconds here because it's generating data every second, and that will kill it. We come back over here. If we refresh their Red Panda console, we now have a sensors topic with a couple seconds worth of data in there. And if we go in, we can see the offset, we can see the partition, we can see a timestamp, a key, which is the sensor ID, and then we have the data payload. And the data payload has 3 items in it, has a sensor ID again, the temperature, and then a timestamp. You can see the key here. We don't have any headers set, but you could also see those. So this is quite nice. If you have different consumers, you can see the consumers in here and the lag. Consumers are essentially the services that are going to be reading from the topic. Okay, so let's move on to the next part of this demo, which is how do we do online machine learning in a Bytewax data flow? So Bytewax is a data processing software that is data parallel. And for each parallel worker, you have a data flow. And what that means is that a data flow is essentially like a set of steps of operations, and those happen sequentially. And instead of those being distributed tasks in a task parallel approach, those are actually all happen on each worker. And so the data is split between workers instead of the data split between, or the task split between workers. This has trade-offs. One of the things that's a benefit is that if your data is highly parallelizable, you can actually have a reduced amount of serialization and passing data around between workers. So you can get some performance benefits there. So anyway, the unit of workload in Bytewax is a data flow. And a data flow has a set of steps in it. And those steps in those steps, you have operators, and in an operator, you have a transformation. Now, an operator essentially controls the flow of data through the data flow. So you have stateful and stateless operators, and they can be of like a map or a filter, or you can have an aggregation type of operator or a windowing type of operator. And then you write the logic as Python code inside of that on how you're going to transform it. So in this specific instance where we're writing a data flow to do some online machine learning, and we're ingesting from Kafka, we're going to have an input, which is our Red Panda input, and we're going to normalize that data, and we're going to use a map operator with some code to normalize the data. Then we're going to have an anomaly detector, and the anomaly detector is it's going to be in a stateful operator because we have our model that we're persisting in state. And in that, we're going to log points to rerun. That's the one step you see above. And then we'll also write the data out to standard out. So let's go check what the Red Panda input and the data normalization looks like. So you can see what the code looks like here. It's pretty straightforward. The Bytewax API, you have just normal Python code and a couple Bytewax objects. So to start with, what we do is we create a data flow object. And then the data flow object has many different methods, and those methods are operators. So it's how you control what's the flow. And inside those operators, you provide the Python logic on what to do with the data, how to transform it. So to start with, we're going to use the input operator. And in the input operator, we're giving it something that's called the Kafka input class. And so Bytewax has a number of native connectors or built-in connectors, I guess I should say, that use or that help you get going where you want to go faster. And so the Kafka input connector, which works well with Red Panda because Red Panda is Kafka API compatible. And you need to provide it with, at the minimum, a broker address and the topic address. Topics are where we're going to be sending our data. So the topic is sensors, as you saw in the Red Panda console earlier. And then we have the broker address here. So you can provide a number of additional configuration parameters. In fact, you can provide all of the ones that are available for the RD Kafka library, which is that lower level C library that the Confluent Kafka Python library uses. And Bytewax Kafka input will take care of having the right worker, if you were to parallelize this, listen to the right partition. The Kafka input in most inputs in Bytewax, you either have to define them as stateful or stateless inputs. And the reason is that certain inputs or data sources are recoverable and certain of them are replayable, for recovery purposes, and certain instances they aren't. And so the Kafka input one is stateful. And so we actually track the progress of data. And what we do is we sync that up with, or the data flow does is sync that up with where the state is. So the idea is Bytewax is a recoverable system. So if in the instance that the data flow crashes or the service crashes, and you had a stateful object that was like weeks of data, if you didn't store state and track progress appropriately, you would have to go back in time and replay the entire stream of data in order to have the correct output. And so this kind of handles all of those nitty-gritty details for you. The next thing we've got going on here is our normalization. So we're doing a min-max scaler, and that's happening within a map operator. So we pass the Python code, which is this function min-max scaler, to the map operator. And here we're giving it the minimum and maximum of 21 and 85, which is predetermined in our case. But in some instances, you'll have to estimate this or somehow predetermine what it is. The output of the Kafka input is the key and the data, and then we add in a new field, which is the normalized. So at this point in the data flow, we have the key, which is the sensor ID, and then a payload that has a timestamp, sensor ID, the temperature, and then the normalized temperature. So the next step, anomaly detector. And the anomaly detector, as I mentioned, is going to happen in a stateful operator, which is called stateful map. And what stateful map is very similar to map, which is map is essentially an instruction, do this to every piece of data. So stateful map is the same as that, but maintain a stateful representation of what's going on. So moving average, or you could use it for a moving average, or you could use it to store a dictionary of items and check if something's been seen before. In our case, we're using it to create a model representation, and then maintain that model representation and change it in some way, shape, or form with each additional piece of data. So the code for that, there's a little bit more code involved because we're creating this class and using it within the stateful map. So what we're doing here is we have our anomaly detector class, which is based off of the river half space trees class. And it receives a number of parameters when you initialize the object. And one of them that is important for us to talk about right now is the window size. So the model is learns on a window size of 30. So after, in our case, 30 seconds, we'll have 30 data points, and those will be used to train the model essentially. And you'll have a moving window. And so you could think of it almost as like a queue, but it's not. It's a model representation. But where for each new data point, you will have one come out the back and a new one come in the front. The way that stateful map works is the data shape is required to be a tuple with a key, and then whatever data or object you have on the other side. And the reason for the key is that in the instance in which we had many workers, we need to ensure that the right data goes to the right worker so we can actually have the correct answer. So in our case, we're having the key is the sensor ID. And so for each time we see a new key, we will create a new anomaly detector. And then for each additional data point that we receive, in this case, temperature reading, we'll update the model. So we use the anomaly detector update method. And inside that update method, what we're doing is we're scoring that value for that value we received. So we're asking the model to score something, and then we're updating the model. So we're learning in the next step there. Once we've scored the data, we log a point, we log a temperature, and then we also determine if it is, in fact, based on our threshold of 0.7, an anomaly. We're going to log a different type of point that is makes it clear to us that there's an anomaly, and then you'll be able to see that. The logging here is happening via the Rerun SDK. So with the Rerun SDK, you're just required to connect to the Rerun service, which can either run in this process or in another process. In this case, we have it running in another process, and we'll go run that in a second, and then we can log points to it. So if we go over to our terminal here, we're actually going to start running this helper again and start generating some sensor data. And then we're going to open up a new set of terminals, and we're going to run, Rerun here. So we have Rerun open, listening on port 9876. And in our data flow, the code of which you can see here, we've actually initialized and connected to this port, localhost 9876. So now we can start logging data there. And it looks like we're writing up quite a significant, I think we might have this turned on in a verbose mode. But so now we'll run our data flow, and our data flow, we're going to be running it with recovery configured. So all we have to do to have recovery configured is add in SQLite directory location, which is the current one. And then we're good to go. We're off to the races. So we run that. We're going to start catching up because we're running from the beginning of the broker. So we're catching up here. And then we're seeing the new points as they arrive. So if we go back to our Rerun, we can see all the data points as they are arriving. And so our temperature sensors are doing just fine right now. What we're going to do is we're going to simulate that this thing crashed. So, oh no, something happened. Maybe bad data or something like that. And boom, things die. So we go in, we go to our Red Panda console. Let's say we found some broken data or some data or something, and maybe we could fix that data, or we fixed our data flow to work with that data. Maybe we just filter it out. Now we'll restart our data flow again. So we run it again. And because we have recovery configured, it's going to just start from, it's not going to start from the very beginning. It's going to start from where we finished. So if we go back here, we can see we started logging on all our points again, and you can actually see we had a couple anomalies while the system was down. So if we didn't have recovery, we probably would have missed those anomalies, or we would have had to make our system go back and start from the beginning and catch up. So that's yeah, that's all I have for today. We can turn this off. Thank you everyone so much for tuning in and listening here. I hope you enjoyed the presentation. If you have any questions about Bytewax, or you have any questions about online machine learning or stream processing, I'm happy to chat. You can find me in our community Slack channel, which is you can find on our website, bytewax.io. If you like Bytewax, give it a shot, pip install Bytewax. You can get started. You can check out our GitHub repo. If you'd like to give us a star, we love the support. It's Bytewax, BYTEWAX /Bytewax.